Hello everyone! So today I'm going to talk to you about the normal distribution. In this video I'll talk about some of the basic characteristics of this distribution as well as some applications of it. Now before we do any math with the normal distribution, we have to figure out what the heck it is. It is probably one of the most used distributions in statistics, so it is important that we get a good foundation of it. The normal distribution is often used to analyze data. Now, let's draw a histogram to demonstrate. We don't need any actual numbers for this scenario, but for the purposes of context, let's say we're analyzing test scores. We're trying to figure out how well students did on a particular test. Keep in mind, this type of distribution measures frequencies or probabilities. We're trying to find out what is the probability of getting a 95%, or what are the chances of getting an 80% on the test. So if we were to draw around our histogram, you'll notice we get an upside down parabola. This curve is our normal distribution. It is also called a bell curve because it looks like a bell. One of the characteristics of the normal distribution is that it is more dense in the middle. The bulk of our data is centered around the middle. So by contrast, this means it is less dense on the tails or the ends. There isn't much data on the sides of the distribution. You'll notice we start at a low height, and then get increasingly larger until the peak, then it goes back to the starting position. With our test scores example, this distribution makes sense. More people are probably around the average, 75%. There isn't much people who got a perfect 100. There's not a lot of people who got a low score, like 50%. Another characteristic is this distribution is symmetric. If we draw a line down the middle of our histogram, you'll notice that the left side and the right side are equal. They are exactly the same on both sides. The line I drew is known as the mean. It is the peak of the normal distribution. It just so happens that in this distribution, the mean and the median are equal. There are many other things that follow a normal distribution, such as height and blood pressure. Now let's draw a generic normal distribution. There are two important measures of the normal distribution. One we already talked about, and that is this center line, which is the mean. Again, it is where the distribution reaches its peak. It is represented by the Greek letter mu. Now, this symbol is used only if we know the entire population. Since that is unlikely, you'll probably see the symbol x bar, which is used for samples. For simplicity, I'm going to refer to mean using mu. Now, the other measure of normal distribution is called the standard deviation, which is the distance away from the mean. It is represented by the Greek letter sigma. Again, this is used if we know the entire population, so you'll probably see a lowercase s when dealing with samples. For simplicity, we're going to stick with sigma. So I said standard deviation is the distance away from mean. So here's our mean, mu. These two lines on either side of the mean represent one standard deviation. To the right, mu plus sigma. To the left, mu minus sigma. The next two lines are two standard deviations away from the mean. Again, the right is mu plus 2 sigma, the left is mu minus 2 sigma. And lastly, these two lines are three standard deviations away. This one is mu plus 3 sigma, this one is mu minus 3 sigma. Just so happens that within one standard deviation, on either plus or minus, 68% of the data will fall in this section. The next section, 95% of the data will lie within two standard deviations. Lastly, 99.7% of the data will be within three standard deviations. This 68, 95, and 99.7 rule comes up every so often in statistics. Now it's time to learn how to apply the normal distribution into problems. Here's an example. A cop measures the speed of cars on a freeway. The speeds are normally distributed with a mean of 65 miles per hour and a standard deviation of 10 miles per hour. What is the probability that a car picked at random is traveling more than 85 miles per hour? Now you notice I highlighted important parts of it. Normally distributed, this tells us we are working with the curve I just showed you. Mean and standard deviation, these are our measurements along with the numbers. Probability, again, normal distributions are used in figuring out the probability of something. More than 85 miles per hour. This specifically tells us what our end result should be. The first step is to write the inequality. This helps set up the problem. So what is the probability? We'll represent that with a capital P, that a car, will represent that by the letter X, is traveling at more than 85 miles per hour. More means greater than 85 miles per hour. Step 2 is to standardize. Because there are many different normal distributions, each with a different mean and standard deviation, we must convert them to the same scale, so it will be easier to compare. In this standard normal distribution, mean is 0 and standard deviation is 1. The formula to find that is z-score, which is another word for standard, equals x, which what we're trying to find, minus the mean divided by standard deviation. In this case, x is 85. Whatever number is in your inequality is what substitutes for x. Our mean is 65, and our standard deviation is 10. When you solve this, you get an answer of 2. Step 3. Draw a normal curve and shade the area. This helps visualize exactly what you need to find. So here's our curve. Remember that now that our distribution is standardized, the mean is 0, and our standard deviation is 1, which is approximately this far. We got a z-score of 2, which is around here. According to our inequality, we are looking when it is greater, so we shade to the right. Step 4, find the percent. You'll need a graphing calculator to solve this. The command is normal CDF, which on a TI-84, it is found by hitting second vars, and it is the second one from the top. I have a new calculator, but on some of the older calculators, it doesn't look like this. But when you enter the information, it is lower, comma, upper. Our lower bound in this case is our z-score, which happens to be 2. Now, our upper bound goes to infinity since it is greater than 2. So on a calculator, I usually enter large positive numbers, say 100. When I hit enter, I get this answer, which rounds to 0.0228 or 2.28%. Step 5. Complete other calculations. Sometimes the problem asks you to use the percent you got. For example, if the problem said, if there were 500 cars on the road, how many got pulled over for going more than 85 miles per hour? We would need to do an extra step. We take the decimal we got, which was 0.0228, and multiply that by the number of cars, in this case, 500. And we got approximately 11. Step 6. Answer the question in context. This is a crucial step. For the original problem, this would be, there is a 2.28% chance a car is traveling more than 85 miles per hour. Then for this scenario, you would say, approximately 11 cars out of the 500 got pulled over for going more than 85 miles per hour. That's all I have for today. Thank you for watching.